All right, polyatomic ions, as the name implies, poly, many, atoms. We're going to start having groups of atoms acting as ions. Okay, so the groups of atoms are going to be covalently bonded, but they act together as a single ion. Okay, so for example, carbonate. It's one of the ones we talked about in the groups of the periodic table and elements. So carbonate is CO3 2-. The carbon and the 3 oxygens are covalently bonded together. That formula is sacred. It cannot change. Do not touch it. Do not change it. It cannot become CO2 because that's something else. That's carbonite. Not the Star Wars stuff, but it's carbonite is CO2. CO4 would be percarbonate. Like, you can't change the number of oxygen. So it's CO3. That is sacred. Don't touch it. Okay? But its charge works exactly the same way. That if I combine it with a sodium with a 1+ charge, I'm going to need 2 of these to cancel out that 2- charge. And so it works the same way. Now, the question is, what do you do when you need more than one of them? Because you can't change the formula. Then you got to write it in parentheses. So for example, aluminum carbonate. Okay, aluminum had a 3+ charge. Carbonate had a 2- charge, so the 2 comes down, and this 3 goes over here. If you just assumed that it was that 3, that would be the wrong formula. Because the whole point is that I needed 2 aluminums, but I need 3 carbonates. This 3 right here doesn't tell me that I have 3 carbonates. This 3 right here tells me that I have 3 oxygens. The only way to tell me that I need to have 3 of this whole thing is to put parentheses around it. Just like when you're doing math, if you just put a multiplication sign in front of something, it's just going to multiply what it's in front of. But if you want it to multiply everything, you have to put it in parentheses. So the same principle works here. When I want more than one of the whole thing, I've got to put parentheses around it. And this CO3, that formula cannot change. Don't touch it. Don't change it. Don't do any of those things. It is just not helpful. Okay, so let's look at some examples. And I'm going to go ahead and give you these polyatomic ions. We're going to look at how to memorize them in a moment. But I'm going to go ahead and give them to you now so that we can work on figuring out how to do the formulas and writing the formulas. Okay, so sodium sulfate. Sodium's 1+, sulfate's 2-. Crisscross. Once again, this 1 coming down does not change that 4. It just tells me that I need 1 whole SO4. So I get Na2SO4. Okay? It's not Na2SO. That is something completely different. It actually doesn't even exist. And so that's just not, you don't want to do that. All right. So the next one, calcium hydroxide. So calcium's 2+, hydroxide's 1-. When I do my crisscross, the 2 comes down here and I need 2 hydroxides. So I've got to have parentheses. Okay. Once again, if you put that 2 behind the hydrogen without the parentheses, that's a completely different formula. That's telling me I've got a calcium, 1 oxygen, and 2 hydrogens if you don't have the parentheses there. It's the parentheses that tells me it's 1 calcium and 2 hydroxides. So that's how it needs to be. All right, same thing here with magnesium phosphate. The 2 goes here, so I've got 2 phosphate groups with the parentheses. 3 comes down on the magnesium like that. And then hydrogen peroxide. This is a weird one that looks like it needs to be reduced, but it's not, because peroxide, once again, you can't change this formula. You can't change that, so you can't reduce this because there's 1 peroxide and 2 hydrogens. And so you can't change that formula. So that's hydrogen peroxide. All right. You can do what I did in high school. And you can simply look at a list of all the polyatomic ions and memorize all of them. It's a royal pain in the butt. I highly don't recommend it. What I would recommend is to look at the pattern of polyatomic ions. Because polyatomic ions, majority of them are some nonmetal combined with oxygen. So if we look at the top of the P block, this is just simply the top of the P block. the nonmetals. You know, staircase runs right on here. Okay, we didn't include tellurium, and we don't have acetine down here. All right, but essentially this is the nonmetal part of the periodic table. So we're going to use this to look at how we do ions. Okay. So oxygen, so first of all, write that down on your notes. First of all, and then leave some space, because oxygen doesn't do this. So we're going to cross out oxygen, because we're not going to look at how oxygen combines with itself. Okay. Notice there's a big bold box right here. And so that big bold box, we're going to say everybody in the box gets 4 oxygens. Everyone else gets 3. So all of those guys get 4 oxygens written with them. And everybody else gets 3 oxygens written with them. All right. And then charges. The charges are going to work the same way. That we're just going to start here. That group 17 is 1 minus. And so group 17 is going to stay 1 minus. Group 16 is 2 minus, and so it stays 2 minus. Group 15 is 3 minus, at least these two are, but until you reach nitrate, NO3. NO3 says no, NO. So it says no, and it wants to start over again, or you can say it even says number 1 to be 1 minus. And then you go 2, 3. So the pattern is 1 minus, 2 minus, 3 minus, start again here, 1 minus, 2 minus, 3 minus. So a simple little pattern. The 4 in the box get 4 oxygens, everybody else gets 3, and the charges are 1, 2, 3, 1, 2, 3. All right, and then naming these, all of them end in ATE. Fluorate, chlorate, bromate, iodate, sulfate, selenate, phosphate, arsenate, nitrate, carbonate, silicate, and borate. So they all end in ATE. Simple. Okay, you've now just seen a simple little way to memorize, let's see, that's 12 different polyatomic ions. And actually from this you can get 48. Because we can add 36 more really simply. So what's going on here is this. So just quickly review. So this is the 8 ions. So the 4 in the box get 4, everybody else gets 3. And then 1 minus, 2 minus, 3 minus, 1 minus, 2 minus, 3 minus. I love this method because all you need is a periodic table. You can look at a periodic table and figure out what this pattern is. You can then look at the periodic table, and even like I always gave my students a periodic table. They always got a paper periodic table for every test. It's a lot of trees, but they need it, and it's essential. And so I give them a periodic table if they need it. And this is something they could write on the periodic table really quick. Like I handed out the test, and it's got a periodic table on the back. They pull the periodic table off the back. They can draw this pattern on it really quick, and they've got it. Okay. So the 4 in the box get 4. Everybody else gets 3. And then the charges are 1, 2, 3, 1, 2, 3. Very simple pattern. Okay. Let's look at it at work. So let's do a couple more here. Sodium sulfate. Okay, looking at your periodic table or looking at your notes. Sulfur is in the box. It gets 4 oxygens. And then doing the pattern 1, 2, 3, 1, 2, 3, it has a charge of 2 minus. Okay, we do our crisscross, Na2SO4. Okay, calcium nitrate. Nitrate is outside the box, so it gets 3 oxygens, and it's the one that starts the pattern over again, so it is 1 minus. All right, and I need 2 of those to make calcium nitrate, so I put it in parentheses with a 2. Magnesium chlorate. Chlorine, once again, outside the box, gets 3 oxygens, and has a 1 minus charge because of the 1, 2, 3, 1, 2, 3 pattern. So once again, do your crisscross, 2 chlorates, 1 magnesium, MgCl3, 2. Okay, magnesium chlorate. Lithium carbonate. Carbon outside the box, 3 oxygens. The pattern's 1, 2, 3, 1, 2, 3, so it gets 2. and then we get lithium carbonate. All right, so that's using the pattern. Okay, now that'd be super, super easy if the only ions we ever had to worry about were the ones that end in ATE. Unfortunately, there are other versions as well that we have to worry about. So we're going to see how that affects the pattern. But really, the pattern is memorizing two things. The 4 in the box get 4, everybody else gets 3. That's the first thing you need to memorize. And the second thing you need to memorize is 1, 2, 3, 1, 2, 3. Two simple rules to memorize, gives you a lot of power without having to just do brute memorization of these. Just look at a periodic table and you can figure it out. All right, so there are variations on polyatomic ions. All right, and there are 3 possible variations. So the 2 I already have uncovered. We have what we just did, what I call normal, and that they end in ATE. So chlorine's outside the box, gets 3, has a 1 minus charge, chlorate. If it's not a polyatomic ion, meaning it has no oxygens attached to it, then it's just the nonmetal, and it just ends in IDE. So you got to remember, if you see IDE as in dog, that means no oxygens. It's just the nonmetal. So we got to kind of keep that straight as we're adding on this polyatomic ion piece. All right, so the first variation is if I have 1 more oxygen than normal. And we call that per-ate. So if I add 1 more oxygen to chlorate and I get the ClO4, then I get perchlorate. Notice the charge is exactly the same. The only thing that's changed is the number of oxygens. I went from 3 to 4. Now the per here, I like to think, is short for hyper. Because if you're more of something, you're hyper, like you're hyperactive, hyper-focused, whatever. So I think of the per as short for hyper. That's kind of how I memorize what it means. So it means I have more oxygen. I've got more, so I'm hyperoxygenated. I'm per-ate. Okay. There's only a couple of these, to be honest with you. Perchlorate is the most common one. I'm trying to think of some other ones that are common, but that's really the only main one I can think of that's fairly common. All right. If you have 1 less oxygen, the ending changes from ate to ite. Okay. Once again, ite is not to be confused with ide. Okay. So you got to keep these two from being confused. Okay. So ite is 1 less. So once again, oxygen just is the only thing that changes. Charges stay the same. Okay. And then the final one is 2 less. If I have 2 less oxygens, then it's hypo. Then the dash and ite. Okay, hypo is the opposite of hyper. So hypothermia is low body temperature. So hypodermic, below or under the skin. Okay, hypodermic, below skin. Okay, so hypo means below or under. And so in this case, it means that's our lowest one down. So hypochlorite is 2 less than normal. So everything in this pattern goes off of this. What is normal? And that's the pattern we just learned, that we just did. Okay, that's why I focus on it first, because it is the foundation. So the 4 in the box get 4, everybody else gets 3. And then the charges are 1, 2, 3, 1, 2, 3. For these, the charges remains unchanged. And it is simply the oxygens that change. Okay? So you just memorize how this goes, and you're good to go. And it becomes more common and natural as you go along. Now, I will say, in terms of polyatomic ions, the 8s, the normals, the reason why I call them normals, because they're the most common. Honestly, probably 90% of all the ions you're going to run into are going to be 8s, or one of the memorized ones I'm about to give you. Okay. So this accounts for the majority of the ions you're going to see. You run into some of these. Like I said, perchlorate is the only one of these I'm even thinking of. Hypochlorite, hyposulfite is another one of these. But these are fairly rare. Both the hypos and the pers just don't show up very often. You'll run into some in your workbook, but that's just simply to make you think and practice that. But in terms of everyday life, you just don't run into the per-ate and the hypoites very often. It is mostly these, the normal ones, with a little bit of these. And so that's just simply what I want you to know there. So once again, let's look at some examples here. Sodium persulfate. Okay, sulfur in the box normally has 4, but that per is in front of it, which means it's going to have one more, so that bumps it up to 5. Okay, so it's SO5 now instead of SO4. Charge remains the same, 2 minus. We write the formula in the same way. Nothing's changed. We do our crisscross, we get our formula. Calcium bromide. IDE means no oxygen, so it's just the bromine. Write it like we did before. Magnesium carbonate. Okay, carbon is outside the square, outside the box, so it normally gets 3. Carbonate means 1 less. Carbonate's 1 less, which drops me down to 2 oxygens. Still has a 2 minus charge, and we do. Those charges are balanced, so it's just MgCO2. Then hypophosphite. So phosphorus is in the box, normally has 4. So when I drop down 2 oxygens, I still have 2 left over. Charge is still 3 minus, and we get the formula Li3. That should be Li3, not Li2. So that should be Li3PO2. All right. So the pattern's great. It accounts for a lot of possibilities. So if you memorize the 4 in the box, get 4, and the charges are 1, 2, 3, 1, 2, 3, and then you memorize per-ite and hypoite, that's 5 things to memorize. And you have a whole slew of ions formulas at your disposal. I think it is by far the cleanest and most efficient way to know these. And I've got to give credit to, this came from a teacher I did my student teaching with outside Atlanta at East Paulding High School, Veronica Cook. She taught me this pattern, and it's amazing. Okay. Now, this doesn't account for all the common ions. There are other common ions. And these, there's no way around it. They have to be memorized. They don't follow the pattern for the most part. And you just have to memorize them. Notice, we also have the one and only, or at least of the ones we're going to deal with, the one and only positive polyatomic ion, which is ammonium, NH4+. So this can replace a metal in an ionic compound. And then these all replace nonmetals because they're negatives. Okay? Because in an ionic compound, you have to have one positive ion and one negative ion. Like you'll never have ammonium with a metal, because that would be 2 positive ions. They can't combine that way. All right? So just looking at these that have to be memorized, they work the same way. So acetate C2H3O2. You will sometimes see in this formula written, otherwise it can be written as CH3COO. It can be written that way because that's what it looks like in terms of how it's bonded. But for me, I usually write it this way. Cyanide, yes, that cyanide is Cn minus. Chromate and dichromate. This is the only time you see a prefix in an ionic compound ever. Is right here, dichromate. Notice it loses an oxygen when it doubles, okay? But the charge stays the same. Hydroxide, peroxide, permanganate, and then oxalate, C2O42-, okay? So just looking at using these, they work the exact same way. You just simply have to memorize them. So chromate is CrO4, the 2-. Formula works the same way. Hydroxide is OH. Cyanide is Cn. And then peroxide is O2. Okay. So they work exactly the same way. So that's polyatomic ions. Once again, practice this. Work through your workbook. Work with the pattern. Make sure you understand it. Check everything with the key. All right? Because once again, it's really helpful. And I strongly encourage having a foundation with this before you add the next element. Because we're just adding one more layer of complexity when we add transition metals in the next lesson. So make sure you understand polyatomic ions before you move on and move into the next lesson. This is definitely not a section to rush through. Because the more pieces you add to it, the more complicated it gets. and the harder it is to put it all together. So let's put it together slowly but surely, and we'll get to the final piece at the end.